So in this session, we will discuss about the IIR filter design from analog filter, Chebyshev filter using either bilinear transformation or impulse invariant method. Okay, so today's objective is IIR filter design. So this is a digital IIR filter design from analog filter. This is a Chebyshev filter from using bilinear transformation or impulse invariant method. So bilinear transformation BLT method, impulse invariant method. This is an impulse invariant method. So you are going to design IIR digital filter. Okay, so in this you can expect the question, compare what is FIR and IIR. So finite impulse response and infinite impulse response. There is a recursive feedback, recursive filter. This is a non-recursive filter. That means there is a feedback in the system. Here there is no feedback in the system. Okay, so finite impulse response, infinite. Similarly, analog filters, Chebyshev filter, one more analog filter we discussed about the Butterworth filter. Butterworth filter and Chebyshev filter. So compare FIR and IIR filter. So if you want a linear phase, then you can go prefer linear phase FIR filter. IIR filter, the magnitude response. IIR filter, less complexity, and depending upon the applications, you can choose either FIR or IIR. Similarly, the frequency response characteristics, if you see the Butterworth filter and a Chebyshev filter, because the ideal one, this is a prototype low pass filter, ideal characteristics. So this is a magnitude response h of j omega. So the ideal, because the Butterworth filters and Chebyshev filters are used to design to approximate the ideal one or closer to the ideal one. So how the pass band will be, how the stop band will be, how the transition band of the Butterworth filter. Similarly, in Chebyshev filter, because these and all we have discussed in detail in the last sessions. So in this session, we are going to concentrate Chebyshev filter. So the Chebyshev filter, there will be a sharp transition from pass band to stop band. So the Chebyshev filter, there are two, type 1 and type 2. Type 2. That in the type 1 filter, so it is type 2 is also called as a, it contains both poles and zeros. Both poles and zeros. So in the type 2, if you see the characteristics, so all pole filters, type 1 is a all pole filter, type 2 is a contains both poles and zeros. If you see the characteristics, so the UK ripple, if you see the characteristics, there will be ripples in the pass band, ripples in the pass band, and flat in the stop band. Ripples in the pass band, flat in the stop band. So there's a These are monotonic characteristics. If you see the type 2, there's a ripples, equi-ripples in the stop band and monotonic behavior in the pass band. So these are type 1, type 2 filters. And we have discussed about that magnitude response, the magnitude square response also. So the magnitude square response is equal to 1 by 1 plus epsilon squared Cn squared omega by omega c. So the epsilon is a ripple factor, There is attenuation constant. You can say it's attenuation constant. Attenuation constant. So it is normally real, which is a real and less than 1. So the epsilon square is equal to 10 to the power, the ripples in the passband divided by 10 minus 1. So you can write epsilon is equal to square root of 10 to the power r by 10 minus 1. So passband ripple. So there is a passband ripple in dB. Passband ripple in dB. And the Cn is nothing but the Cn polynomial coefficients. The Cn Chebyshev cosine polynomial coefficients. Polynomial coefficients. If the another formula I'll write, depending upon the specification you can choose. If you refer the Nagarkani, in that 1 by AP squared, the passband gain minus 1 to the power half. So this formula also you can use. So A is the gain of the passband H frequency. Gain of the passband H frequency. Passband H frequency is a omega p. Okay. The higher order polynomial coefficients are for small values of n. For small values of n, you can use this formula directly. For small values of n, so n is the order of the filter. Cn. The Cn is a Chebyshev cosine polynomial of order n. Written of Chebyshev cosine polynomial coefficient of order n. Okay. For small values of n, so the Cn of x is equal to the cosine function n cos inverse x, where the x is less than or equal to 1. The hyperbolic function cos h of n cos h inverse of x, where the x is greater than 1. So the initial values C0 of x is equal to 1, C1 of x is equal to x. The higher order polynomial coefficients, higher order polynomial coefficients higher order polynomial coefficients may be determined using the relationship Cn of x is equal to 2x Cn minus 1. This is C Cn minus 1 of x, this bracket Okay, minus C n minus 2 of x. Okay, for example, if n is equal to 2, if n is equal to 2, okay, the Cn of x is equal to 2. So this will be 2 minus 1, 1 x. This will be x, no? So 2x. So 2x squared minus C0, that is 1 x, that is 1. So the Cn of minus 1x is x into x2 x squared minus 1. C2 of, this is C2 of x. This is C2 of x. Similarly, C3 of x. If you want to find C3 of x, so 3 minus, okay, so you substitute this one, C3 minus 1, 2, C2 of x. This, okay, into this one. So, into x. So, 4x cube minus the Cn of minus 1. So 3 minus 2, 1. So 1 of x. So you will get 3x. This one will be 3x. So C2 of x and C3 of x can be calculated. The higher order polynomials can be calculated by this equation. If the maximum passband triple is specified and the epsilon can be calculated, can be determined, and if attenuation is specified, for example, another formula, if attenuation is specified, different formula, then if attenuation is specified, okay, and if the maximum possible ripple is specified, okay, attenuation at the particular stop and frequency is specified, the order n can be calculated. Okay, the order n can be calculated by using this formula. So remember that the formulas n is equal to cos h inverse square root of 10 to the power 0.1 alpha s minus 1 divided by square root of 10 to the power 0.1 alpha p minus 1. So divided by cos h inverse of omega s by omega p. So another formula, if you refer the Nagarkani with respect to the possible gain, okay, depending upon the, if it is given the dB, you can use this formula. If they given gain in the passband h frequency, you can use the formula. So n is equal to cos h inverse 1 by epsilon 1 by a squared minus 1. Okay, if the attenuation, if the gain is specified in the stop and edge frequency, divided by cos h inverse omega s by omega p. So use this formulas. Okay. If the gain is specified in the both passband and stopband, you can use this formula. N is equal to cos h inverse. It is 1 by a squared minus 1 divided by 1 by ap squared minus 1 to the power half divided by cos inverse of omega s by omega p. Okay. So similarly, the next important topic is what is the relationship between Butterworth poles and Chebyshev poles. Chebyshev poles. So Butterworth poles, how the poles are located and how to determine the determination of angle of poles. Angle of poles is a pi k. So how once if we know the Butterworth poles, so the geometrical relationship is the geometrical relationship. Okay, if you see the poles how it is located for Butterworth filter is circle. The poles are located in circle. The poles are located. Butterworth poles how it is located? The poles located in the circle. Okay. The Chebyshev poles. The Chebyshev poles are located in the ellipse. Ellipse. So this is a circle. This is a circle. This is a ellipse. Ellipse. So the Chebyshev poles are located in the ellipse. So this is a geometrical relationship between the Butterworth poles and Chebyshev poles. So once the Butterworth poles are known, then you can translate into the Chebyshev poles. Okay. So there are various steps how to determine the various and poles for stability determinants of angles of poles pi k, generally pi k is equal to what is the pi k, which is equal to k pi by n for n is equal to odd and pi k where k plus 1 by 2 into pi by n for n is equal to even. Okay, so once the values of n is known, once the values of order is known, n is known, once the n is known, okay, a straightforward way to translate, okay, to translate the Butterworth field poles to Chebyshev poles. So since there is a geometrical relationship between circle and ellipse, the poles lies in the circle can be translated to the ellipse. It is a Chebyshev poles. So this is because of the geometrical relationship between the Butterworth poles and Chebyshev poles. So the design parameters, you can write the design parameters. For first, okay, A value, you can determine the A value is equal to A. A design parameter is A is equal to 1 by n sine h inverse 1 by epsilon. Okay. So the real part of Chebyshev poles. The Chebyshev poles, Chebyshev design, how to determine the poles. I'll tell you the various steps. First, the Chebyshev design, you take the valid Butterworth poles. Butterworth poles. That is, for example, B1 is equal to A plus JB and B2 is equal to A minus JB. B2 is equal to A minus or C. We will take C. 2 C and D will take C. Okay, C plus, so A plus, okay, we'll take the same. Okay, A plus JB, A minus JB, the Butterworth poles. Then you second step, you find A. So A, we know that this is A. What is A? The design parameter. The design parameter A can be determined by using, once the n is known, sin h inverse 1 by epsilon. Find A. Find A, the design parameter A. The third step, you find tan HA and cos HA. Then multiply the fourth step, multiply the real part, multiply the real part, multiply the real part by tan HA. So this is called normalization. This is called normalization. So multiply the real part by tan HA. Then that is a how, so B1 and B2, no, this poles. So for next, the normalization will be B1 dash. So multiply the real part by tan HA. A tan HA plus JB. The other one is B2 dash. The new poles are C. So C into tan HA. We'll take C and D. Okay. C tan HA plus JD. So normalization, the real part multiply real part by tan HA. Now denormalization. The next one, fifth step. Now denormalized by multiplying by multiplying cos HA for the desired Chebyshev poles. For the desired Chebyshev poles. So Chebyshev poles C1, which is equal to multiplied by cos HA. Now denormalize this one B1 dash. So A tan HA plus JB, and the C2 will be cos HA, multiply cos HA, C tan HA plus JD. Multiply the real term. Okay, this is a real term of this filter. So real term of the Chebyshev filter, the new poles will be, so the Chebyshev of these poles multiplied by the cos HA. Okay, then once the poles are determined, once the poles are determined, we can find out the transfer function h of s is equal to the transfer function, the analog transfer function h of s equal to p divided by s plus c1 and s plus c2, s plus c3, and there we go. So what is p? The p is equal to, the polynomial coefficient p is equal to the concatenation of c1, c2 and c3. Multiply these three, c1, c2, c3. Okay. Okay. We'll take one problem. Okay. Find the order of the filter using, there is a order of the filter, IIR filter from analog filter, Chebyshev filter. Find the order of the filter from analog filter, Chebyshev filter using, okay, bilinear transformation or impulse invariant method. Okay, any method you can use. So the given specifications are, given specifications passband ripple is given 0.5 dB and stop band attenuation is given, stop band attenuation is equal to 20 dB at 10 kilohertz, and cutoff frequency is given, cutoff frequency is equal to 2 kilohertz. And till the steps you compute properly using calculator and cross check the values. Okay, you can use this formula. The attenuation is given. If the attenuation is given, you can use that formula directly. The attenuation in dB is equal to 20 log 10 epsilon plus 6 of n minus 1 plus 20 n log omega by omega c log 10. So the stop and attenuation is given, then write, so omega s by omega c. So you can substitute the values, attenuation in dB. So 20 is given, attenuation is given 20, so this is equal to 20 log 10. The epsilon, you find epsilon, so epsilon is equal to square root of 10 to the power gamma by 10 minus 1, that is the ripples in the pass band. So ripples in the pass band is given 10 to the power 0.5 by 10 minus 1. So epsilon is equal to 0.349. Okay, so you cross check, use computer, use calculator and cross check the value, then you proceed to listen the next step. The next step, find the order of the filter n. So what is the epsilon value? 0.349 plus 6 minus 6n. Okay, minus plus 6n minus 6 plus 20 n log of omega s by omega p, that is 10 by 2 cutoff frequency. So minus 6n this side, then you calculate this value. I think minus 9.136. This is minus 6. This is minus 20. Okay, plus this value and this value you can calculate. So this value will be 19. So this is minus 6n. Minus 6n. which is equal to minus 9.135. This is 135 minus 6 minus 20 plus this will be 13.978. So again you can calculate this 19.979 n 35.135. Please cross check the values. So n is equal to 1.758. So n is equal to approximately this is equal to 2. Order is 2. Okay. So find the order of the filter. So either you can use the order of the filter, different formats given. So depending upon the given specification, determine the order of the filter. Once if you determine the order of the filter, next the design various steps. First we'll find a value. A is equal to 1 by n sin h inverse 1 by epsilon. Correct? The design parameter 1 by n. So 1 by n is equal to 2. Substitute n is equal to 2 and sin h inverse 1 by the epsilon 0.349. So now a value is equal to 0.887. This is also a cross check. So every step use calculator and cross check and you can proceed to listen. Then tan HA, can use calculator. Tan HA will be use tan HA, that is a 0.71. Then cos HA, second step cos HA, to find cos HA will be 1.42. Okay. Now the Butterworth poles, Butterworth poles, how to determine the angle of the poles. Once if you know the uh, n is known, then the Butterworth poles can be translated using the geometrical relationship. Okay, so n is equal to 2, which is n is equal to even. So now the determination of poles will be pi k. This is a normal Butterworth poles. Butterworth poles. Pi k is equal to k plus 1 by 2 into pi by n, where k is equal to, that is where k is equal to 0, 1 up to 2n minus 1. So 0, 1, 2 into 2, that is n is equal to 2 minus 1. So it is equal to 0, 1, 2, 4, that's 3, 0, 1, 2, 3. So pi 0 will be, there is pi 0, pi by 2 by 4. So this is by 2, this is 2. So this is equal to pi by 4 by 2. So pi by 4. So this is equal to 45 degree. 45 degree. Okay. Similarly, pi 1 can be calculated. Pi 1. So 3 pi by 4. 3 pi by 4 will be 135 degree. And pi 2 will be, the angle of the poles can be determined by 5 pi by 4, which is equal to 25 degree. And similarly, pi 3 is equal to 7 pi by 4, which is equal to 315 degree. For stable transfer function, we use only, for note, for stable transfer function, we consider only pi 1 because between the stability, for stability, we consider the angles between 90 degree and 270 degree. First, then between 90 and 270, these two poles, the pi 1 and pi 2. So this is the stable poles. Find out the stable poles. These are called stable poles. So determination of poles and how many poles are will be considered for the stable poles. So for stable transfer function, we are using only pi 1 and pi 2. So because we are considering only these two stable poles between the angle 135 degree and 225. So these two range between this 90 and 270. Okay, so P11. So now the P11 can be calculated. That is e power j pi 1, which is equal to cos 3 pi by 4 minus j sin 3 pi by 4 Okay, so minus 1 by root 2 minus j, that is a cos 3 by 4 plus j sin 3 by 4 or minus 1 by root 2 plus j 1 by root 2. Okay, similar the other poles p12 is equal to e power j pi 2, so which is equal to cos 5 pi by 4 plus j sin 5 pi by 4, so which is equal to minus 1 by root 2 minus j 1 by root 2 minus j 1 by root 2. So now the both poles are, but with poles are minus 1 by root 2 real part j 1 by root 2. Now, once if we know the Butterworth poles, then how to translate into Chebyshev poles? Okay, so the given the step 1, the Butterworth poles are B1 is equal to minus 1 by root 2 plus j 1 by root 2. That is equal to, you can write minus 707 plus j 0.707. This is a B1. The other pole is B2. B2 is equal to minus 707 minus j 0.707. This is step 1. Step 1, B1 and B2. Step 2, then step 2, we know the find A. Already we find A. A, so which is equal to already find A. So third step 3, find tan HA and cos HA. So already we find all the values. A values, what is the A value? 0.89. A values, this A value, tan HA value, cos HA values. So we can write the values here. Okay. So 0.89. So find these values 0.89. Okay, I'll write it here again. Tan HA is 0.711. So cos HA is 1.42. Step 4. So the new poles. So what are the steps? Various steps. So the normalization. Multiply. Step 4. Multiply the real part. Multiply the real part by tan HA. And write down the step again. So this is a normalization. Normalization. So B1 dash is equal to, what is the tan HA value? 0.71. So multiply the real part. What is the real part? Minus, this is the real part. This is the imaginary part. So the real part, multiply the real part minus 0.707 by tan HA value. This is 0.711 plus, okay, B1 dash plus J 0.707. Send the new Butterworth poles. Multiply the B2 dash, which is equal to real part multiplied by, so which is equal to here minus 0.5 plus j 0.707 for B2 poles. So B2 dash is equal to minus the real part multiplied by the tan HA, okay, minus j 0.707, which is equal to minus 0.5 minus j 0.707. So B1 and B2 are determined. Then step 5. What is the step 5? Step 5 is denormalization. Denormalization. So what is denormalization? We have to multiply by multiply cos HA for the desired Chebyshev poles. So now C1 and C2, C1 is equal to multiply cos HA by the of your A tan HA. I like the formula again here plus JB. Similarly, C2 is equal to cos HA of this is C tan HA plus JD. Okay, so now C1 is equal to this cos HA value is 1.42 multiplied by this function b1 dash and b2 dash. Okay, so there is minus 0.5 plus j 0.707 which is equal to minus 0.71 plus j. So C2 will be 1.42 into minus 0.5 b2 dash minus j 0.707 which is equal to minus 0.71 minus j, which is equal to, it is actually minus, you can write minus 1 by root 2 plus or minus j finally. Minus 1 by root 2 plus or minus j. The Chebyshev poles are, the Chebyshev poles minus 1 by 2 plus or minus j. So now the step 6. Step 6. So the transfer function can be written h of s equal to p by, so s minus of this one, so s plus 0.71 minus j, and the other one is s plus 0.71 plus j. Okay, this is h of s is equal to, right, 1 by s minus of this one, minus 1 by root 2 plus or minus j. So minus of plus 1 by root 2, okay, plus 1 by root 2 plus j and plus 1 by root 2 minus j. So you can write either way. So now the p is equal to, you can write p is equal to c1 and c2. So c1 and c2. So you can write p is equal to square root of 0.7 squared plus 1 squared which is equal to 1.5. So p is equal to 1.5. So p is equal to 1.5. So h of s is equal to 1.5 divided by this s plus 0.71 minus j into s plus 0.71 plus j and minus j. Use impulse invariant method. So once if we know the Butterworth poles due to the geometric relationship between the Butterworth and Chebyshev filter, we can translate the Butterworth poles into the Chebyshev poles. Okay, then you can write the transfer function which is equal to this 1.5 by s plus c1 and s plus c2. So now impulse invariant method, we can use impulse invariant method which is equal to, it is a h of s 1.5 divided by, it is a s plus 0.71 minus j into s plus 0.71 plus j, which is equal h of s equal to a by s plus 0.71 minus j plus b by s minus s plus 0.71 minus j plus j minus j. Okay, so you determine the values of a and b for this. So a is equal to and 1 and b is equal to, sorry, a value and b value 0.75j and minus 0.75j. So from this you can write the simplified, another simplified one. So you can apply the impulse invariant method directly and you can determine the h of z. Convert h of s into h of z. Okay, the unlocked transfer function, so either, so normalization and one more point. So either you can use directly. So instead of this, if you find this way, and I think h of s will get h of s equal to, check, 1 by s square plus root 2s plus 3 by 2. Okay, then denormalization, put s is equal to low pass filter, put s is equal to s by omega c, and omega c is omega c. So what is the omega c formula? 2 pi fc. Fc is given, no, cutoff frequency 2 pi into the cutoff frequency is given, so 2 kilohertz 10 power 3. So omega c is equal to that is a 4 pi into 10 power 3 radians per second. So you can multiply, you will get the cutoff frequency 12.56 kilohertz. Okay, so from by using impulse invariant method, this one can be written as, this h of z can be written as 1 divided by 1 minus e power minus 0.71 minus j to z inverse plus, okay, that is a 0.75 j divided by 1 minus point e power minus point, so plus, okay, 0.71 plus j, this minus z inverse. Okay, so you simplify these two, then find h of z. So you can write this one more step. I'll write 1 divided by 1 minus e power minus 0.71 into e power plus j equal j 1j into z minus 1. Okay, plus 0.75j divided by 1 minus e power minus 0.71 into e power minus j into z inverse. So this value will be 0.49. 1 minus 0.49, okay, of 0.54 plus 0.84j z inverse, 1 minus of. So finally you can multiply these two, you will get, cross check the values here, you will get 1 minus 0.49, 0.54 minus, this will be 0.54 minus 0.84 j z inverse, 1 minus of 1 minus 0.49. So this term will be, so finally You check h of s is equal to 0.615 z inverse divided by 1.168 minus 0.52 z inverse plus 0.067 z minus 2. So then you can realize the system. Then final step will be a realization of IIR filter using that from 2. You know the coefficients, so the delay elements are from 2 delay elements. Okay, you can implement the coefficients. So the other problem for practice I'll give. So problem, you practice this problem. So design a Chebyshev filter. Okay, Chebyshev, that is a digital IIR low pass filter you design from analog filter Chebyshev filter using impulse invariant method. Impulse invariant method, you take t is equal to 1 second. So from the given specification, the specifications are given in this. Is a 0.9, the h of e per j omega then equal to 1. So draw the frequency response and specify the parameters omega 0.25 pi and the h of e per j omega 0.24, so 0.5 pi less than or equal to omega then equal to pi. So realize this in direct form, two structure. Okay, so I'll write down the steps here. So here AP is given, so the passband gain is given 0.9 and the stop band gain is given 0.24. Passband gain, this is passband gain AP, this is AS. Okay, then this is omega P. Omega P is given 0.25 pi radians per second. So and omega S is given, this is 0.5 pi radians per sample, 0.5 pi. Okay, so for impulse invariant method, so omega P is equal to omega P by T, this one here. Similarly, omega S is equal to omega S by T. So what is omega P? So 0.25 pi by 1. So 0.25 pi by 1. Okay, this is radians per sample. Radians per sample. So 0.25 pi, which is equal to 0.7854 radians per second, omega P. Similarly, omega S is equal to 0.5 pi by 1, which is equal to 1.5708 radians per second. Now find the order of the filter using this formula. N is equal to, the previous case the specification is given in different way. So in this case, with respect to the passband gain and stop band gain, we can choose this formula. So cos h inverse. So what is the formula? 1 by the stop band gain a squared minus 1 divided by 1 by ap squared minus a squared, ab squared minus 1 half, so this, okay, divided by cos h inverse of omega s by omega p. So the value of n, use calculator and compute the value of order of the filter n. It is equal to 0.1077. So n is approximately 3 you can take. Okay. So our, as once if n is known, our rule is once n is known, okay, the determination, because the determination of poles, first determine the Butterworth poles. So by k is equal, if n is odd, so if n is odd, pi k is equal to, sorry, pi k is equal to k pi by n. N is equal to odd. So what is k? Where k is equal to 0, 1, 2, n minus 1. 0, comma 1. N is 3. 2 into 3, 6 minus 1. So 5. 2 into 3 minus 1. So 0, 1, 2, 3, 4, 5. 2 is a 6 minus 5. So k is equal to. So now you can determine the pi k equal to 0, pi 0, pi 1. You determine pi 0, pi 1, determine. Okay, pi 2, pi 3, pi 1, pi 2, pi 3, pi 4, 0, 1, 2, 3, 4, pi 4, pi 5. Okay, determine the poles. I leave it to you. Then after that, once you determine the poles, what are the poles are considered for the stability? Stability. For stability, the angle between 90° and 270° poles will be considered. Then you form the transfer function h of s. Okay, h of s, that is a transfer function. So you check, we're getting 0.516 to leave it to you. Okay, s squared plus s cube